Hello and welcome to our next Shell Eco Marathon 2020 virtual learning session. Today with Altair Engineering. My name is Norman Koch and I'm the Global General Manager of Shell Eco Marathon. I want to start off by thanking all of you for your flexibility and understanding as we evolve Shell Eco Marathon due to the impact of COVID-19. As the situation continues to change, the health and safety of our Shell Eco Marathon participants and organizing teams remains our top priority. Given this status, we are excited to have you all with us in this digital environment to kick off our virtual learning session, all from the safety of your homes. Today, you will be hearing from Eric Larson from Altair Engineering about creating lightweight, optimized designs. Altair is a global technology company that provides software and cloud solutions in product development, high-performance computing, and data analytics. Altair supports Shell Eco Marathons by supplying licenses, training, and support for Altair HyperWorks to all teams competing in Shell Eco Marathon. Eric is a technical account manager for education in Altair Engineering. He's been with Altair for over 13 years. He studied mechanical engineering at the Michigan Technological University and has 30 years of experience in product design and analysis. Welcome, Eric. And we look forward to hearing from you in just a few moments. But before we get there, just a couple of housekeeping items. We would, of course, like this session to be as interactive as possible. So if you have any questions throughout the presentations, please go to the website menti.com on your browser and enter the code shown on the screen below. On Menti, you'll be able to post your question, but also see the other questions and give a thumbs up to the questions that you think are important to answer, so they raise in the queue. If by any chance you have any issues accessing Menti, you can also post your questions on the YouTube comments to the right of the live stream on your YouTube. Eric from Altair will then be answering your questions, and please come up with really good questions so we can put Eric to the test here. Just in case, because this is a live stream, and for any reasons we run into technical difficulties, please bear with us as we try to fix the problem as quickly as we can. With that being said, Eric, that's all from me. So please, Eric, kick off the session for us. Over to you.
Excellent. Thank you very much, Norman, for that nice introduction. And I am pleased and proud to be here. I appreciate all that Shell has done for bringing these sessions to us in these times where we can't meet in person. And I know it's not the eco marathon we wanted to have, but it's a great alternative that keeps us all safe at home and ready for what's going to come at us next year. So a bit of history about Altair and our relationship with Shell. We've are celebrating our fourth proud year of being a partner and supporting of the Shell Eco Marathon. But even before that, for many, we've been supportive of super mileage teams and competitive design teams in general. Prior to our becoming an official sponsor of the Eco Marathon, we sponsor Vehicle Design Award and we sponsor teams with free software. And with our CFD structural and optimization offerings, we are a great fit to improve vehicle performance in the case of mileage, fuel economy, and energy efficiency. And before we get kicking off with some slides, I just wanted to show you real quick how you can achieve one, or how you can get one of these sponsorships. So you're just going to want to go to our website, altairuniversity.com. Altair University is going to be your main source for everything dealing with our software. You see our free student edition is right here. But we do offer sponsorships to teams. To get to the team sponsorship, it's just under the students category right here. And right here under student competitions. That's going to take you to our site where you can request a sponsorship. And requesting a sponsorship is nothing more than just filling in some data into this field. It will take you 5 minutes to do so. And then we'll be in touch with you, and typically within a week, usually no more than 2 weeks, we're going to provide you with as many licenses as you want and need to support you. We will also back that up with trainings, with mentoring, with sometimes on visitations, and we will help you use our software to make a better vehicle. So on to the presentation. What I want to do is I'm going to show you about 4 slides. I don't like to bore my audience with slides, but I think 4 of them gives a good story as to what Inspire is all about, and the entire rest of the presentation will be dedicated to a live demonstration that will get you started with Inspire. So Inspire is a tool that will allow you to easily, conveniently, and very, very accurately perform structural analyses and, even more importantly, lightweight optimizations of your designs. This is an example of the process that we go through with Inspire. This original part right here is a support arm for a suspension on a heavy truck. This picture does not do it justice. This part is huge, and it is very, very heavy, as most cast parts are. And because of its design, it's in fact way over-designed. This thing would never fail. And that's great and all, but it does mean that we're carting around too much material. There's an opportunity to make the part strong enough with safety factor built in to achieve our goals, but yet not overuse material, making the part greener because it's more efficient to make, it's cheaper, uses less material, and it's better for the environment because it allows for greater fuel economy, energy usage due to its lighter weight. So using Inspire, and we're going to show you how to go about doing this, you can take the original design. Inspire will intelligently, through a simulation-driven iterative process, determine the material that's necessary and the regions where material is not necessary. And then an engineer can take this information, engineer a part that in this case is a 55% mass reduction from the original design. Now, that's not the only benefit that you can get from a simulation-driven design project. Much like this aircraft door hinge that was developed by Eurocopter, their original process took 3 months to go through. It was a manually iterative process where they're going to go through and come up with a design. They're going to test it virtually or physically, revise that and over and over and over until they get a part that weighs about 9.15 kilograms. Took 3 months to design. But when they did the same process using Inspire, they were able to come up with a part that was not only lighter weight, coming in a bit over 7 kilograms, but reduced the design time from 3 months to an amazing 3 weeks, because we're developing a design that's simulation driven, allowing simulation to make some of the difficult decisions for us or help us make them. Another thing Inspire can do for you is make sure that we're adhering to design for manufacturing, a critical part of any design process. The best, most designed part ever, lightest, strongest part is completely useless to us if we can't manufacture it. And so Inspire allows us to include manufacturing constraints that guarantee that whatever design we ultimately come up with, it can be created, manufactured with our desired manufacturing process. So this had a tremendous weight savings and was manufacturable. And last but definitely not least, in the case of this part, which is a satellite antenna bracket, holds an antenna in a proper orientation. One of the biggest and most key features of any design is optimized design is it has to meet the criteria that you set forth. And in the case of launching something into space, that's some pretty serious criteria. This part is going to see some tremendous forces and thus tremendous stress upon launch. And as once something is put up in space, there's very little we can do to go and fix it. If this part were to fail and break or bend in any way, that antenna would not be oriented properly, and you could potentially lose the entire satellite as a result of it. But I'm happy to announce that not only did we see a 42% weight reduction in the design, this part did survive the launch and is holding the antenna exactly where it should be, making this a very useful satellite. So, as I said, enough of the slides. Slides are good as a brief introduction, but from here on out, we're going to go full-on demonstration, and the information that I show you should be enough to get you up and running with Inspire. So let's take it from this. Let me clear this out. So before we get into the software, let me just give you or get into loading up a part, let me just give you a brief overview as to the structure, the setup of the software. Now, when you run it for the first time, whether you get the free student edition or even better, a sponsorship, it's going to load up like this, and you're going to see the screen like this. One of the very first things that I always do is I come up here to View, and I turn on the model browser and the property editor. And as we get into these designs, you're going to find the invaluable information that's going to provide you right here. And yes, we lose a bit of the graphic real estate as a result of having them up, but the benefits that we get, I feel, far outweigh the loss, a little bit of loss of the screen. So along the top, we have our pull-down menus and our ribbon selectors. We, of course, have our file pull-down where we're going to be able to create a new or open a recent. We'll see all my recents here, save things, do screen captures, alter our preferences. Edit, we have our undo and redo, cut, copy, paste. View, where we can manipulate some of our views, turn things on and off, and we do support Python as a scripting language. And then the rest of these are what we call ribbon selectors. So in kind of the way that Windows has gone, we've gone to a ribbon-based structure where each one of these different sections is going to represent a different type of manipulation within the model. The first of which is geometry, so all of our geometry creation and manipulation. Next, we have our structure, where we're going to be able to set up our analyses, where we can fasten, joint, load, and set all the parameters necessary to ultimately move over to the analyze and the optimize. Motion, where we can do motion analyses, and while we don't have the time to get deep into motion analysis, I'll let you know what this is all about. Lead into manufacture, where we can do casting and stamping studies, and then finally we even have our own printer, 3D printing simulation tool in here that will allow you to take your design, set it up on the printer, orient it, create supports, slice it, and then export that to be printed, and even analyze the 3D print. Now, this is only for metal SLS type printing, but polymers and extrusion will be included ultimately. But that being said, let us actually open up a model and let's get to work on this. Let's see what we can do with Inspire. So I'm going to come here. I'm going to open up a model, and just to show you, when I come to open a model, these are all of the different file types that we support. And we support the native file for any of the popular CAD systems that are out there, as well as some intermediate formats, with IGES, STEP, Parasolid, STL. But I'm just going to open up this Parasolid file that I use for demonstration purposes. And this is the file that we're going to kind of walk through the entire analysis and design process. So this is, if you remember that slide that showed the aircraft door hinge, this is the bracket, holds it both to the frame of the plane. Two of them are going to be aligned like this, mounted to the frame. And then two of them will be aligned like this, mounted to the door, and the aircraft door hinge will mount between them and allow that kind of interesting motion you get from an aircraft door, where it kind of comes in, tilts, goes out, and lays up against the aircraft. And we want to see if we can improve this design. Ultimately, we're going to take this to an optimization and come up with some sort of lightweight but strong design. But before we do that, it is important, at least in the case of this part, to understand where we are at right now. We want to see the behavior of this part as the design is, and then use that information to help us build an optimization and understand the results of an optimization to make sure we're creating a better part through optimization. So before we get into that, one of the things that people always are going to want to know is how to manipulate the model. Inspire has its own mouse manipulation parameters, where I can hold down the middle mouse button to do what we call a trackball rotation. It's rotating around that little X in the middle of the screen, and so I can rotate it like that. Holding down the right mouse button gives me a pan, so I can move it around. And then using the scroll wheel to zoom in and out, pulling the scroll wheel towards me zooms in, pushing it away zooms out, using the pointer as focus. So whatever I hold my pointer over, that's what I'm going to zoom in on. Now, any GUI-based software is going to have its own mouse manipulation, and it seems like every single different software out there, whether it's an FE software or a CAD software, seems to have their own different take on mouse manipulation. Everyone does it a little bit different than everyone else, which sometimes makes it rather difficult to move from one software to another. And if you've ever used multiple softwares, multiple CAD softwares, or CAD and FE software, you know exactly what I'm talking about. But we want to make the transition from CAD to Inspire as seamless as possible. So all you need to do is come to the File pull down here, come to Preferences, and come to Mouse Controls, and you can see we can change the configuration of the default mouse, where I can make the right mouse button do whatever I want it to do, middle, left, and right, and then my manipulators here, Control, Shift, and Alt. Or even better, if you're familiar with the CAD system, all you have to do is come up here to this default, select it. We're going to get a list of all the popular CAD systems there. And as soon as I select one of them, it's going to change all of the buttons to that manipulation style for that particular CAD system. So if you're moving from SolidWorks or Inventor or CATIA or UG or Pro-E to Inspire, that little change is going to make it a seamless transition, because you'll feel right at home as you try to manipulate your model and screen, and you won't suffer from the problem trying to move from one scheme to another. Now, I don't use a CAD system, so I'm going back to the default. Click OK, and I can rotate it like this. To do an analysis, the very first thing we're going to need to do is establish a material specification for this part. And you'll see over here in my model browser, if I click the part, it's going to give me a whole bunch of information. It tells me the mass of the part, 4.27 kilograms. And if I come down here, it's made out of steel. Well, this is an aircraft part, and very little in an aircraft is made out of steel. When it comes to aircraft parts, we much prefer our friend aluminum. So I can click here, or what I prefer is just to right-click on the part, select material, and I can see the entire material database that comes with Inspire. Everything from steel AISI 304 all the way down through plastic nylon is a material that comes with the package with the software. And you'll find many, if not most, of the very popular material specifications, including aluminum 7075 T6, a popular aviation aluminum. But if you have a special material, or you've got the exact specifications for your material, then what I encourage you to do is come here to the Structure ribbon, come to Materials. By default, it's going to list all the parts and the material that they're made out of. I can look at the material library that comes with software, and then I can come here to My Materials. See, I have a number of custom materials for air material, material 1, material 2. All I have to do is click plus. It adds a new material to the bottom. I change it to reflect the Young's modulus, the Poisson's ratio, the density, the yield stress, and the coefficient of thermal expansion for that material. And then I have a brand new custom material. And you see for Young's modulus, which is a pressure, it's asking for MPa, so megapascals. And the reason it's asking for that is because I am in, if I look down here in the lower right corner, I'm in the MMKS, which is the millimeter Newton second scheme with a kilogram mass. If I select down here, I can change this to any of the popular unit schemes. So if I want to be working in meters, I can just come up here and pick meter Newton second. If I want to be working inch pound force second, I can do that. And all I have to do is select any of these. It will automatically update everything about my model, the material specifications, the overall sizes of the part, the loads, temperatures, everything will be automatically adjusted. But I'm going to still continue working in the millimeter Newton second, and so my stresses, or my Young's moduli, are going to be in terms of megapascal. And when I now come here and right-click to material, you see that new material 3 is down there at the bottom. So by all means, add your custom materials to this. But I'm content with my my steel here. I'm sorry, with my aluminum here. And you can see I gave it a relatively large weight savings already, as it was set for, or with steel, it was 4 point something kilograms, and by changing it to aluminum, I brought it down to about 1.5 kilograms. Now that the material is defined, I need to begin to set the parameters to do an analysis on this. And this is going to be a linear static analysis. That's the type of analysis that that Inspire can do, and it's utilizing the OptiStruct engine in the background, so we can be 100% confident in the results that we get out of here. And then, well, OptiStruct itself does support some nonlinear materials and specifications. Right now, at least, Inspire is strictly linear. So linear static analysis means I have to make sure that my part stays within the linear range of the material, and it's a static analysis. So it can't be free to move on its own. I need to lock it down somehow. And to do that, I'm going to come here to my structure tab, and I'm going to come over here to the loads icon. Now, unlike many softwares, some of Altair's as well, we didn't go the standard icon route. Most icons are about a square inch by a square, quarter inch by a quarter inch. Not very descriptive as to what the icon. We wanted nice, large, descriptive icons that told you exactly what function you were getting into. And to do that, what we opted to do, to be able to include all the many functions that are within Inspire, we created these multi-function icons, which means loads, depending upon where I pick on the icon, I get a different type of load. If I click down here on the bottom, I get a support. If I click this arrow, I get a force. If I click here, I get a pressure. If I click here, I get a torque. So that one icon supports actually 4 different types of loads that I can put on here. And they're all very descriptive and very obvious as to what they mean. So my supports are going to be what holds it in place. If you're familiar at all with FE, you'd know this is a constraint. And if I select my supports, my pointer gets a little modifier on it, a little cone, indicating that I'm now creating supports. And it says I select a point, an edge, a face, or a hole. And so I come here, excuse me, and I can pick a face, an edge, a point, or a hole. I'll start by just picking a face. If I select that face, it's going to put that constraint icon right where I picked. But the fact that this entire geometry, this entire face highlights red, that tells me that this icon is controlling this entire face, and it's rigidly held in place. That face is not going to move at all. So it's as if I glued or welded this to something grounded, and the rest of it can deform, but it can't move. Now, if I want to alter the configuration of that, all I have to do is double click on it, and I can free up any 1 or 2 directions, making a slightly more complex or slightly more robust constraint. If I click here, that arrow turns green, and now this is telling me that this part is free to free to move in what amounts to the Y direction. So we get these roller wheels on here showing us the direction it can move in. If I double click on this again and grab my move support, I can orient that however I want it to be. I can rotate it in increments of 5 degrees, or I can type in a specific value and it will orient to that. And now you see the roller wheels are pointing to 37 degrees off of the Y-axis. So I've altered the orientation of that. If I double click it again and pick this arrow as well, now it's free to move in plane, but not out of plane. And that's represented by this little caster wheel here. So even our icons are going to highlight and show you exactly what that is doing. So there's never any doubt as I look around my part. And I could do the same thing to a line or a point. But actually what I want to do, so I'm going to highlight that and click on it, and it's going to go away. What I want to do is simulate how this part is mounted in the aircraft. And the way that this part is going to be mounted is it's going to bolt through these 6 holes here. And I'm going to put my supports, I'm going to come back to supports, and now I'm going to pick a hole, and you see I get the little modifier showing it's a hole, and I can click in these, and I get a slightly different constraint icon. And the reason it's slightly different is because Inspire is recognizing that these are holes, and holes provide a unique constraining opportunity, because most of the time, holes are constrained with either a pin or a bolt. And if constrained in that manner, that means that it can never move perpendicular to the axis of the hole. But if I double click on it, you see it will allow me to free up rotation about the hole and free up translation along the axis, but never translation normal to the axis. So I can develop a very accurate representation of whatever I'm using to constrain this part in place. And now with all of these on the holes, my part is nice and rigidly constrained, but the rest of it is free to deform. Now, as I move on here, I'm going to start creating some loads in just a second, but I just want to remind you that as we're moving along, if a question pops into your head and you want to make sure it gets answered, please proceed on to menti.com. Once you get there, you're going to enter that code, which is now showing on your screen, the 562036. Put your requests in there, and from what I understand, you can thumbs up them to make them more relevant and move them higher on the list. And I'm very much looking forward to getting to your questions at the end of my presentation. We've allotted a nice amount of time, 35 minutes, so we hopefully can get through everyone's question and get all of your questions answered. So while it's on the tip of your mind there, pop on over and put the question in there so we can make sure we get to it. Okay, so with this now, what I'm going to do is I'm going to come back to my loads icon. And with my loads icon, I'm going to grab this force here. And I'm going to take that and come over here, and I can, just like with the constraint, I can apply this to a point, an edge, a face, or a hole. And I'm going to apply this. If I apply it to a face, a surface, again, it's going to put that point there, that force where I clicked it. But because it's all red, it's going to apply that force to the entire surface. And this is the value of that force, to 224.11838 newtons. And that's going to be spread out evenly across that entire surface there. If I want to change the direction, just like with the constraint, I can click the move icon and rotate, orient this any direction that I want. Or if I don't know the angles, I come here, open this up, and I can put in the vector components. Now, these are just for orientation. The magnitude is separate, but this will allow me to orient that in whatever direction I need to orient it. I'm going to delete it, though, because where I'm going to apply the load is actually in the center of this hole here. So make sure I'm on my force still. When I move to the hole, my mouse gets that little modifier showing me I'm putting a force on a hole. And if I click that, it's going to put a force right dead smack in the center of that hole. But the entire inner surface of that cylinder is going to highlight red, which means that that force is going to be connected to and evenly distributed across the entire inner surface. And I can orient this in any of the cardinal directions, plus or minus. The one I want is going to be Y minus, and then I can give it a value. So I'll type in, say, 2000 here. Click enter, and I get 2000 newtons. So I've just created a 2000 Newton load in the negative Y direction. We can see the vector orientation right there. And what this is going to do is represent a situation where this is mounted on the door and the door is open. So the weight of the door is going to be pulling down on this. And I'm going to see how this part behaves with that 2,000 Newton force pulling down on it. But that's not the only situation that this bracket can be in. The door is open and pulling down on it, or in flight, the door is closed, and the hinge is going to be exerting a force to keep that door tightly closed. And I want to represent that as well. So I'm going to come back up here to my force. I'm going to click on that hole again, and it gives me another arrow, and it's in the right direction, but I needed to go positive. And now I can give this a force as well. It defaulted to whatever I put in as my default force. But say, for instance, you don't know what that force is in newtons. You say you got this from somebody and they told you that it was 500 pounds force. Well, if I come here and type 500, of course, and click enter, it's going to be 500 newtons. But if I do the same thing, if I come in and type 500, and then as opposed to clicking enter, type in LBF, the abbreviation for pounds force, and click enter, automatically convert that to whatever force unit I'm currently working in. So whatever unit I've got here, it's going to convert that, and that works for distances, times, masses, forces, pressures of the different units that we can possibly enter. It will automatically convert it to whatever unit system I'm currently working in. So save you a trip to Google to make the conversion for you. So that's it. From here, I could go and run the analysis. But before I do, let's talk about some of the other ways I can load this up. This is just a standard point load. I can do a pressure load. If I select that, it's going to apply that pressure to the entire surface, 1 megapascal to that entire surface. And now if I hover over it, it's going to tell me not only the pressure, but the equivalent force, 7,100 newtons, that's going to apply to that. So take into account the actual area of that. So let me delete that. I can apply a torque. I can apply a force displacement. So let's say, for instance, I need to test this. We've got a part, it's sitting on an airplane, and I don't know the force that's acting on it when the doors hang open. And I don't really have a tool to measure that. But I do have somebody who can go out there and tell me that this point right here moves 4 millimeters in the negative Z when the door is open. I can click on this in force displacement, click on that point, type in 4 millimeters, indicate the orientation. And now what will happen is, even without any force on here, it's going to take and make that node move 4 millimeters, and then we can see whatever stresses result from that, not even knowing what the force is, but knowing what the displacement is. I can do G loading. So G loading is going to be based on the gravitational acceleration. I can click that and say, okay, I want a 5G load on this part, and it's going to do that. I can do angular velocities and accelerations. We'll get to gravity in a little bit. And I can apply temperatures. So if I put temperature on here, you said delta T. So irrelevant of whatever temperature it's at right now, we just assume it to be neutral temperature. It's going to increase the temperature of this 150K. And then as a result of that thermal load, we're going to get a thermal expansion. And because the part is deforming, we'll get a stress as a result of that. And if I had made that negative 100K, we get a contraction and we get stress as a result of that. So we can add just about any type of force that you're looking to do. They do have to be static forces. We don't support dynamic forces in these static analyses right now, but later I'll discuss a way that you can kind of do a pseudo-dynamic analysis. And then I can even come here and add non-structural masses. Non-structural masses are a tool when the mass of something is important, but not the direct configuration of it. So think muffler hanger. You go underneath your vehicle, there are a number of hangers that are keeping your muffler from dragging across the ground. If I want to do a study on those mirrors. I don't need the complexity of the entire muffler system. I just need to know what the center of gravity of it is and the mass of it. I can put that center of gravity there, that non-structural mass at the center of gravity, and then connect it to my part, and I can analyze it by putting a mass there. It's another way of loading it up. And that's pretty much it for the way that we load a model up. The next thing I do is come over here to my Analyze. I'm going to click the little play button here. It's going to open up my analysis window. With my analysis window, the first thing I can do is I can name that analysis. Very useful if you're doing multiple studies. I can control the global element size, and we'll talk a bit more about the meshing. You don't have to worry about the meshing at all. It will take care of all that for you. But if you do want to control some aspects of it, we'll talk later about how you can do that. Then I can ask or request normal modes if I want. So I want to know what the first 10 normal modes are in an unsupported model, or I can get the first 10 incorporating load case 1. So I'll leave that on there. And then I can do buckling analysis. So I can, again, request my buckling modes and which load case I want to use. Indicate whether I want it faster or more accurate. More accurate, if you're familiar with meshing, is going to provide a quadratic or a second-order tetrahedral element. Far more accurate, but do take a bit longer because the increase in... or I can go faster, which is a first-order linear tetrahedral element, which will get my result faster, but will tend to have more stress and less deformation because they are stiffer. So only do that if you really need some rough answers quickly, but not something you'd want to bank on there. We'll come back to contacts. Gravity, if I want to incorporate gravity or not, I can click yes, and now gravity will be included, but I need to make sure gravity is pointing in the right direction, so I can come back to gravity here. Orient that gravity properly, and it will default to the Earth standard gravitational acceleration. We can just go ahead and leave that at that. But this is a relatively compact little part. Gravity is not going to have that much of an influence or no discernible influence on it. So I'm not going to muddy the model up by including gravity. And then I can come down and include the load cases. And I see I've got one load case here. So this load case is going to take all my forces, all my constraints, and run an analysis on it. But that's a bit of a problem. So coming back to here, I need to close this for a second. Coming back to here, I said I had this indicating this would act when the door is closed, or be the force when the door is closed. This is when the door is open, but that can't happen at the same time. And if both of these forces are acting at the same time, I'm going to get some sort of vector result here, which is non-realistic. These forces can never happen at the same time. So before I run it, I need to come back here to my loads, to this little chart icon here in the corner, and this allows me to create load cases. Load cases are essentially studies. I said I had a door open and a door closed. Well, I can click here, select the constraints or the supports that I want, and then select the force I want, deselect that there, and now I get two independent studies. They will run in the one analysis that I do, but I will get two separate results, one for each of them. But more importantly, when I get around to doing my optimization, the optimization will take both scenarios into account when it, or into its study when it does it, still acting independently, but making sure that my part is optimized to support both of those load cases. And I can continue to add load cases as I want. So say I wanted to study it, assuming bolt 2 and 3, my support 2 and 3, let's pretend that they failed. So I won't even include them. I'll just grab the other 4 and that load right there, or force right there. And now I'm doing that study right there. And I can continue to add these as I see fit. And when I come back to my analysis, you see it includes all load cases and they're all turned on by default. And from here, I can just run the analysis. So if I click run, it's going to pop up this little status window. And what's going to happen in the background is Inspire is not just muddled together geometry based element or meshing element analysis tool. It's actually a geometry front end for our high end analysis, meshing, and pre-processing tools. So what's going to happen is it's going to take this part and it's going to send it to our tool called SimLab, which is going to create a very, very high quality tetrahedral mesh. Then it's going to send it to HyperMesh, our preeminent preprocessor, which is going to set up all the parameters for the analysis, and then send it off to OptiStruct, our analysis optimization tool that we've been developing for 20 some odd years now, to make sure that we get the most accurate results possible. So you're utilizing our high-end enterprise level software, but you're doing it in a very easy to use interface. And had I not been talking through the entire thing, I probably could have had this thing running from a completely empty screen, bringing in the geometry and setting everything up. I could have had it running in about maybe a minute and a half to 2 minutes. And then I wait another 2 or 3 minutes for the analysis to be done. And in a grand total of about 5 minutes, I can get a very, very accurate linear static analysis on a 2-load, 3-scenario model. And again, I might remind you that as we move along here, if you have any questions, and hopefully you've had some come to mind, go on to menti.com, enter that code 562036, and ask those questions, and we'll get to them as soon as we're done. And this should be just about done here. And as soon as it is, I'm going to get my little reward. A little green flag is going to pop up here, and that tells me that my analysis is done, and I can take a look at the results. What we'll do after that, we'll analyze the results. We'll realize, or we'll determine from them where we stand with our current design, and then determine if this is appropriate to move into optimization and see if we can come up with a better simulation-driven design. And there you go. Almost as if on cue, I get my little green flag. I click that. It takes me directly into the post-processing tool here, where I can see all 3 of my load cases plus my normal modes. I can see all the different result types I have: displacement, von Mises stress, percent of yield, factor of safety. My animation, where I can see how the part is going to behave. And before you get a little concerned about this aircraft part, which looks like it's being made out of some sort of rubber, realize that we automatically scale up our animations. If we look here on our legend, we can see the maximum displacement we're getting is 5.047 e to the negative 2 millimeters. So, 5/100ths of a millimeter, which obviously is not being represented there. We scale up our transformations or scale up our deformations so we can see them. And if I click this, you get scaling it up 376.5. And the reason we do that is if it came up and was a 1-to-1, this provides me almost no information whatsoever. To even see the animation, see the deformation, I have to zoom in, and just looking at this isn't going to give me the information I need. So we take care of the trouble of scaling it up for you so that we can see the behavior of this. But no matter what your scale factor, these values here are 100% correct. I can come down to my von Mises stress, see my stress here, see the stress as a result of each one of my load cases and the behavior of each load case. And most importantly, I can come here and take a look at my factor of safety. So what factor of safety is going to do is going to compare the results that I have here to the yield stress value that I entered into my material definition. So if we come here and we look, aluminum 7075 T6 has a yield stress of 413.7 megapascals. And coming to factor of safety, I'm going to find out how many times higher or lower I am from that. Now I can use this little slider here, and let me come back to von Mises stress for a second. I can use this little slider to isolate values. You can see as I pull this up, it's getting rid of the lower stress values, allowing me to focus on purely the high stress values. And if I change it to factor of safety, since factor of safety, the better things are higher, I can slide this down. And as soon as I get off the 6, the highest value on the scale here, the entire model disappears. So this is telling me my entire model has a greater than 6 times factor of safety. And while initial thought for an aircraft part might be, wow, that's great, if only the entire airplane had a 6 times factor of safety. Well, I'll tell you, if the entire plane had a 6 times factor of safety, you'd be lucky if you could bring luggage with yourself and the pilot, because that's all that's getting on that aircraft, because it couldn't possibly lift anymore. So a more reasonable factor of safety is typically between 1.5 and 2 times. And the fact that the thing has a 6 times factor of safety tells me one very important thing, and that is this part is way, way over designed. And there's a lot of room for improvement. Even with the 1.5 kilogram mass of this, which isn't that much, even with that relatively low mass, this part has too much material in it. And so I can make this lighter, make my plane more efficient, and allow it to carry more cargo or more passengers, the things that hate to ride on a plane, by taking out excess material. It's a waste to fly aluminum around or excess aluminum around. So this analysis tells me I'm good to go with optimization. Before we move on, though, I do want to show you the normal modes. So if I come here to normal modes, I get displacement and strain energy. So strain energy is going to show you where it's straining most, and displacement. And it then shows me the values for each one of my frequencies. So in a completely free frequency analysis, I can see that my part has a lowest mode of 4,300 or 4,500 and 39 hertz, which more than likely is sufficient to guarantee that my part is safe when put on the plane, experiencing the vibrations that, say, the engines or other things provide. And then I can see all the way up to the 10th mode. They definitely get more complex, with my absolute favorite being the 10th mode. I like it. It's kind of getting interesting there. So we can see how this part is going to vibrate at which specific frequency. So with that done, the next step would be to move on to an optimization. But before we get into that, we need to discuss one more thing. And to do that, we're going to have to kind of take a sidetrack from our part here. I'm going to open up this part, which is Dre. And the reason I open this up is because this part is made up of about 25 or 30 different individual pieces. And so I get a lot more information in here, and I can come through and see all of these. But the big question becomes, what happens when I have a whole bunch of other pieces, other parts? How do I make sure these are going to behave as a full assembly and not as just a bunch of individual parts which are going to fall apart as soon as I try to run an analysis? Well, the short answer is, you don't need to worry about it. Any two solids that are touching are automatically bonded together. We can visualize that through, in the structure tab, this context icon here. It's going to represent all of the interfaces between all of the different geometries, all the different solids. It's going to represent them as blue surfaces. And so I know from front to back, side to side, this entire part is connected together. I could put some constraints on here, I could put a load on here, and I would get results, because this entire part will act as it's connected together, which is great. It means I don't have to worry about anything. But while the results will be relatively accurate, they're not as accurate as they could be, because we're going to end up with an interesting situation in this case right here. Okay, so we can see what's going on. So this is bonded to this. That's great. Excuse me. I must be boring myself. That's bonded to that. That's great. But this should not be bonded to the top plate and should not be bonded to the lower plate. The load path should proceed through the bolts, which even themselves are bonded to the top plate and to all the part they go through, because they are geometric representations. So that means that any force put on this arm is going to push or pull this surface with it, because it's bonded to it, which is not accurate. So I can do better. And the key in this case to doing better is to get rid of all of the graphical or the geometric representations of the connectors, the bolts. So I can come over here to my model browser, and I'm going to scroll down, and I'm going to shift select those, click delete on my keyboard, and then grab everything that says hexagon socket and delete that. And now I've gotten rid of all of the different bolt representations, because I want to use Inspire's bolt representation. If I select this, it's going to automatically find holes that are a candidate for a bolt or a screw to go through. A bolt will be applied to anything that's a through. So this runs through the top plate, through this arm, the bottom plate, and comes out the other end. And so I'm going to bolt on that. But here, I'm getting a hole through the top plate, but only partially through the end of this arm here, what we call a blind hole. And so it's going to create a screw, and when I click fasten all, I get screws in my blind holes, I get bolts in my through holes, and most importantly, if I come and take a look at my contacts, these are now green. Green is what we call contacting, or more commonly, a sliding contact. It means these two surfaces can't part from each other. They can slide along each other, and that's going to force the bolt itself to take up the load transmission as that begins to move. Now, I said they can't separate from each other, but if I were to, say, put a significant amount of force on the bottom of this and push up, this potentially could separate from the bottom plate. But as it stands right now, it won't do that. But I can allow for that by coming back to my analyze here, or optimize, and we'll talk about that later. And you'll see contacts, sliding only, and sliding with separation. Sliding only is the default, because it does take a bit more process time to incorporate separation. But if I know that there might be separation, I can select that. And now what will happen is it will constantly analyze the contact force here. And if that contact force goes negative, indicating this wants to pull away, it'll let it. And I'll get a very, very accurate representation of the way that that contacts. And interesting enough, this is some pretty complex stuff. It would take quite a while in a standard preprocessor to do a lot of the things that we're just automatically doing here. One last thing, I said it's going to put a bolt through the through holes and a screw through the blind holes. The only difference between the two is the bolt is going to come through and it's going to mount at the top and the bottom, representing the bolt head and the nut. The screw is going to mount at the top, and then it will connect all the way through the blind hole portion, which is going to represent having screw threads on this. So the threads would engage with the geometry, or with the part, and we're going to represent that by connecting that screw to the entirety of the blind hole portion of the connector. Excellent. So with that discussion of multiple parts behind us now, the next best thing to do is to move on to the optimization portion of this and explore how we're going to go about taking our original aircraft door hinge, bracket, and seeing about coming up with a better design, because the opportunity is there to do that. So the first thing we're going to want to do is discuss the concept of what topological optimization is. Now, you may have heard of topological optimization, you may have not. One of the key catchphrases these days is additive geometry. Or no, what is it? Not additive geometry. Can't remember the name of it. It's something along that time. Something along those lines there. But no matter what it's called, it's effectively taking a shape and determining what of that body of material is necessary to create or to support whatever requirements you put onto the part, and then get rid of the material that doesn't contribute to what you're looking for it to do. Easiest way to understand the idea behind topological optimization is to think of sculpting. So when an artist wants to make a sculpture, they're going to take a block of some material, marble, wood, whatever, and they're going to kind of see inside of it. They're going to think that inside of there is a statue, whatever they want to represent, and then they're going to go about getting rid of all of the rest of the material that's around it. So the statue was there inside the material. The artist's job is to get rid of all the extra material. And that's exactly what topological optimization is. Topological optimization carves away material not based on aesthetics like a sculpture, but based on the necessity of that particular piece of material to contribute to what you want it to. Generative design, that's the word I was looking for. Generative design is the new kind of key phrase that everyone's using, and essentially it was developed by people who were doing what we've been doing for a very long time, topological optimization, but wanting to refer to it as if it was some sort of brand new concept. So whether it's called generative design or topological optimization, we like to call it topological optimization because that's the scientifically accurate way to describe what's going on. Generative design is just a new catchphrase to do what we've been doing for 30 years now. So to get a good optimized part, just like to get a good statue, you would never carve a statue out of a statue that already exists. And the last thing that I want to do is optimize this part exactly as it is. I would have very little freedom for creating a part because it would be limited to the body of what I've got right here. Because just like carving a statue, you can't make a statue that's bigger than your original block of material. And you can't end up with a topologically optimized design that's bigger than the design space that you provide for it. So ideally, what we like to do is provide it with a big block of material. And to do that, we need to get rid of some of these lightweighting features that were put there already. This could be done in your CAD system, and by all means, go ahead and do it in your CAD system if you're most comfortable with it. But I will tell you some of the tools we have here in Inspire are actually easier to use than the CAD systems. So if I come here to simplify and I come to holes, what holes does is it automatically looks for holes, and if I click on them, they disappear. They fill in. I like that hole. I want to get rid of it. What I do want to get rid of these little pockets here. It's not seeing them as holes, but if I double click on it, it finds it. If I click again, away it goes. And it makes it very, very easy to fill these in and get rid of that lightweighting feature that I don't need. Now, the next feature I don't need, they went and carved off these corners, again, to lighten it, get rid of some of the excess material, perhaps with a little bit of engineering behind it, in a lot of cases arbitrarily, or just what look good, or run an analysis, and if it's blue, doesn't have any stress, we just cut it out. But I want to do this with simulation, so I'm going to take and I'm going to pull these out, and I can do this with push-pull. Push-pull allows me to push and pull a surface, and if I do a slope surface like that, it'll bring it out to a corner. And now I have a nice big block of material like I'm looking for. And this is an ideal shape for optimization. Big, bulky block of material that's going to allow the optimization tool to carve away the unnecessary material. I don't want to muddle it up by putting fillets on here. That I can do after the simulation phase. The more features you put on there, the longer it will have to run, because it will have to create smaller elements to accommodate that. So I create a big block of material. But what I don't do is I don't put material where it would interfere with something else. So that door hinge is going to mount on here with like a clevis mount. It's going to, like a U, it's going to come down here and over here and up here, and a pin is going to go through here. So I'll leave these devoid of material because I can't have material there or it would interfere. As that rotates, the hinge is going to kind of slide in underneath here. So I need this to be free of material to make sure that it doesn't interfere with the hinge. I need these little cubes here to be free of material, not because I necessarily need a cube, but I need to make sure there's no material there. So I put my wrench in to grab the top of the hole, drop the top of the bolt there. I have something to grab. I get a wrench in there. So I don't know whether I'm going to end up with a cube here, but just not having material there is enough. So you put in as much material as you can and leave out material that's going to interfere with something else. You fill the design volume. And so this is a great design space. And the optimization code, when we get to setting that up, is going to take and it's going to carve away at this material, revealing the part within that is the least amount of material to achieve whatever goal I ask from it. But one problem I have is this will carve away material. But what about my hole here? If I don't have that perfect cylinder there, I'm not going to be able to properly mount the door hinge to it. And if I don't have this perfect cylinder here, I'm not going to be able to put a bolt through and tightly lock this in place. There are regions of our model that are critical to the design. And we're going to need to segregate those out, partition those out using this tool right here. If I click partition and I click that, you see it builds this little buffer around there, this little partition around there. I can say how thick I want it to be. And now fairly separate solid from the rest of my part. But we know, as we discussed before, it's connected because it's contacting it. But this is entirely separate solid, which means I can right click on the main body here, indicate that as design space, that which the solver can carve away from. But this gray region here, it's a no touching. It cannot touch that. It has to be left exactly as is. So I can preserve my non-negotiables. Typically, these are the regions where I'm loading or connecting this part to something else. And speaking of connecting to something else, I can't lose these holes down here, so I'm going to come back to my partition. Because of the way that it's detecting this entire feature, if I were to click that, it actually protects, builds this partition around the entire box and my bolt hole. And I don't need that. I don't need to protect that box. I just need that box to not have material in it. So I'm going to come to my partition, and a little trick we have is to just separate this from the rest of it by holding my control key down. You see I got that little minus there. And when I select these two surfaces, they go away, and now I can pick that, and I just get those little sleeves. Same thing on these two. 1, 2, 1, 2, and rotate it around here. 1, 2, and 1, 2. And now I have a perfect part for optimization. I've protected my important locations. I've expanded my design space out to fill the entire possible volume I can have, and I'm giving the optimization code all of the tools it needs to develop a topologically optimized, lightweight, strong part. One last thing I'm going to do before I actually set up the optimization is to come back to my structure tab here, and I'm going to take a look at this right here, my shape controls. First and foremost, my manufacturing controls. So I said a part is useless if we can't make it. And these allow us to specify limitations based upon the standard methods of manufacture, which are casting, stamping, and extruding. And then we even have an additive constraint, but we'll get to that in a second. So the three main manufacturing processes have always been casting, stamping, and extruding. Casting and stamping have a limitation because a die is involved, and you're either wrapping or shoving material and bending it into the die in a stamping process, or taking and filling that die with a liquid or semi-liquid material and allowing it to cool. Somehow we need to get the part out of there. And the only way we can do that is to have these things here, which are called draft angles, which allow that mold to come off of it, and that thing that's working against the drag direction. In this case, we've got a split draw where we've got two shapes coming together, and so it can go out, but those regions that are angling out have to meet at the partition line. And then finally, we've got our extrusion constraint. Extrusion, you can think of it as shoving a semi-molten material through a shape. If you're a kid and you ever had one of those really cool Play-Doh toys where you would take the Play-Doh, you'd put it in a bucket, you'd slide a little shape over the top of a nozzle, and as you push down, it would shove the Play-Doh through the holes, and you get little spaghetti noodles, little stars or tubes or whatever. Little did you know you were practicing extrusion manufacturing at a really young age. And the key feature about extrusion is it always has a constant cross-section because it's being shoved out of a shape. The vast majority of the use of the extrusion is when you're going to be laser cutting or water jet cutting a part because, well, you always end up with the same cross-section if you laser or water jet cut something. Finally, this little guy on the end, it's our overhang constraint. It's the most recently added manufacturing constraint. And that just deals with additive. When you're doing additive manufacturing, because it's a layer by layer process, in many cases, you can't have one layer sticking too far out over the layer below it, or the material is just going to sag and not work. So this allows us to define the maximum angle of overhang and guarantee that even our additive or 3D printed parts are as accurate as or manufacturable as possible. So that's it for our manufacturing constraints. The last icon, or the last thing we have here, are what we call symmetry controls. Symmetry, we come to symmetric. If I click my design space, it's going to put these planes of symmetry there. And what's going to happen is it's going to try to, as best as it can, maintain symmetry on the part. Now, it's not going to do a real good job in the z-axis because it's not symmetrical that way, and it sure as heck isn't a very good job in normal to the x-axis. But the y-axis is what I want. I want to make sure that this part is interchangeable. I want to make sure that I can flip this part over and use it on the other side of the aircraft. I want one single part for both the frame and the door mounting on the port and starboard sides of the aircraft. So this will guarantee that across this plane, my part will be symmetric, and most important because one of my loads coming in this direction, which means it would strengthen this side of it at the expense of this side, but this guarantees that it will be symmetric. Now, because I brought this up, I lost my loads and my constraints. I just brought it up as geometry again. And I'm not going to bother going through and recreating them because time is short here, and we know how to do that. And I'm actually not even going to run the optimization. The optimization goes pretty quick, about 5 to 7 minutes, but it's 5 to 7 minutes we don't have. So I'm just going to talk about the optimization parameters. Then we'll see the results and wrap this up pretty shortly here. But we need two main things for an optimization: an objective, which is what we're shooting for. And the two objectives we're going to talk about are maximize stiffness, where it's going to try to make the part as stiff as possible, and minimize mass, where it's going to try to remove as much mass as possible. Well, the other thing that we need, because optimization can be tricky and can be sneaky, is a constraint, a limitation. And the reason we need that is because if I were to say to the optimization code, make this part as stiff as possible, it's going to look at this and say, oh, there you go, it's as stiff as possible. Well, the most material is going to be the stiffest part possible, so it's not going to do anything. So to keep it honest, I need to provide some sort of constraint on that, and the constraint for a maximized stiffness is a mass target. What I'm going to say is I want this part to be as stiff as possible, but you only get 30% of this entire red volume to do it. 70% of this volume has to be thrown out, and the remaining 30% has to be distributed in a way to make the part as stiff as possible. And after many years of experience, we've determined that 30% is a good starting point, which is why it's default. But you could find out that it's leaving enough material or it's leaving too much. So you can run iteration after iteration, altering these. The other option is minimize mass. And in this case, now I'm not telling it how much to get rid of. I'm saying get rid of as much as possible. And again, I'm left unconstrained. It's going to look at this and get rid of the entire design space and say, there you go, there's your optimized part. So we have to keep it honest by putting some sort of constraint in there, limitation. And in this case, the constraint is a stress constraint, or more specifically, a stress safety factor. So I think we're going to use 1.5 on this. So what's going to happen is going to take that yield stress, it's going to divide it by, in the material, divide it by 1.5 and say, I cannot see stress above that value. So as it begins to remove material to minimize mass, less material means higher stress. And as if it starts violating that 1.5, it's going to leave material there and seek elsewhere. And that's it. Everything else in here is exactly the same as it is in the analysis. With the, I guess, with the one exception is I can set a minimum frequency. So we'll take a look at frequency as well. I'd click optimize. Like I said, it would take about 5 to 7 minutes to run. So we'll pull the old baking show trick where they show you how to make the cake and turn around and grab an already completed one out of the oven. And my already completed cake is this right here. This is the optimized design. This is where I would want to be. And I can double click on this, make it a little bit more robust, widen these struts up a little more. And to make sure that this meets my requirements, I just click Analyze here. And this will take just a minute to run the analysis. And while it's doing that, what I can also do is, right now, my non-design spaces are geometry, but the rest of this is still a mesh. To get this out of the software, get it into a CAD package, it's as simple as double-clicking on it, click Fit NURBS, and it's going to NURB geometry in there. This is now geometry, and I can bring it into whatever CAD package I want. It's, of course, it's going to be a little slow getting out of there because I've run an analysis at the same time, and you can see that that's now my part. My other option would be to manually generate polyNURBs. I get a little bit cleaner polyNURB by doing a wrap, and it'll detect the cross section. I can draw these little tubes here, and then bridge them together by selecting surfaces, and it will fill the part, and I would fill the rest of that in. Turn off these polynerves because I've got my results, so we can see how well this part survived. You'll see we have a fair amount more stress on here, especially in the little angles, the little corners. That's okay though. I said I left those corners sharp intentionally because I know I can resolve them by filleting this afterwards. The most important thing is if I come here to factor of safety and I begin to bring this down, you'll see I've got a lot less factor of safety. Not all the part is over 6, but the critical and key thing is as I get down here to 1.5, which was my limiting factor, just about all of it is gone except for these, which again I'm going to limit by putting a fill down there. And just to show you what somebody who's quite skilled at the polynerves can come up with, this is the part that somebody generated from this directly within Inspire. So you can create the geometry from Inspire or bring it into your CAD system and generate it from there. And with that said, please remember menti.com. If you have questions, I'm wrapping up my presentation right here, so we're about to move into the Q&A. So please, as it's showing at the bottom of the screen there, menti.com, code 562036. Ask your questions there, and I would love to answer them, and I hope there's some really good ones that we're going to get to. So I'm going to pass the baton back over to Norman, who's going to kind of finalize things up here, and then he's got the whole list of all the questions you've asked, and he's going to see how well he stumped me with some of your questions, and we'll see what we can do. So take it, Norman.
Well, thank you so much, Eric. What a wonderful and insightful presentation. Really great explanations, and amazing to see what the software can do. So thank you very much for these thorough explanations and showing it us live in the software. The questions have been coming in, and I would like to remind the teams who are listening today, please keep them coming in. Send them in either through menti.com. You see the number at the bottom of the screen, or write them in the box in the YouTube on the YouTube channel. As you follow the stream, if you're logged in, you can also enter them there. First of all, I think a question that the most of the users will want to know, Eric, do you need any computing power to run Inspire?
That's a great question, and I'm glad that came up first. One of the great things about Inspire is it is optimized, no pun intended, to utilize whatever it can get from a processor and a graphic card standpoint. And what that means is it is not a processor hungry or graphic hungry tool. I've seen this and helped install this software on something as slim as a Microsoft Surface tablet computer, which I guarantee you is not the most processor intensive. As with any software, the higher, the more powerful the processor, the more RAM you have, the greater the graphics card you have, the faster it's going to run, perhaps the smoother it's going to run. But pretty much any computer that has the capability to run Windows 10 is going to be enough to run Inspire.
Okay, thank you. And getting into a more specific question about the software, can you just explain again and elaborate how can this software be used in conjunction with other CAD systems like Inventor or SolidWorks or others?
Excellent. Yeah, so what we like to do is we like to consider ourselves kind of a design partner with the CAD systems. CAD systems are great tools for generating solid geometry, and everything seems to be going kind of the way of solid geometry these days. So you're going to create your designs initially in a CAD system. Then you can bring them into Inspire, and bring them into Inspire is as simple as just going to File, Open, and as you saw when I showed you that list, support the native formats of pretty much every popular CAD software that's out there. Or if we don't support it, if some odd software that we don't quite yet support, Parasolid Step and IGES. You can bring those directly in there. So consider Inspire kind of the next step of the design process. Even if the CAD software you have supports limited analysis, ours is going to be a bit faster. It's going to be easier to do, and it's going to be far more accurate. So you do your design in your CAD software. You're going to bring it into Inspire. You're going to manipulate it either in the CAD software or Inspire to get that nice, large, bulky design space. You're going to run your optimization, do that quick polynerbs, auto-generate polynerbs, then bring it back into the CAD software and let your CAD software kind of be the other bookend at the other end of this to then take the recommendations that Inspire is going to give to you and create that great part that's going to be 50, 60, 25, whatever percent less massive than it was before.
Probably related to this question is this one here. Are there options to load parts as an assembly?
No, there's no options. It just does. If you have if you have an assembly, so I know the one I'm most familiar with is SolidWorks. I've got the SLD part for the solid part, or SLD ASM, and I know CATIA also has CAT part and CAT ASM. Just open the ASM file in Inspire and it will automatically take care of it. So you don't have to set anything. It knows enough to do that already. It'll bring in the assembly. It'll bring in all the parts of that assembly. And while I don't have a part to demonstrate it, whatever sub-assemblies you've got going in there, all of your organization, all of your file or your part names, assembly names, they're all going to be maintained in Inspire. So the good answer is you don't have to do anything other than just open up the assembly file, and Inspire takes care of all of the rest for you.
And staying with the assemblies, another question is asking for the assemblies, is there any option to simulate friction?
Not in what I've shown you so far. So I didn't really get a chance to show much about the motion capabilities, but the motion capabilities. If you'll grant me just a minute here, I'll open up my my software again here, and I will bring up a model that shows the motion capabilities here. So this there we go. This flap and spoiler model. This is our motion analysis, and I've coupled this with an analysis. Oops, I need to come to motion. But when I create my motion analysis, I can, like I said, couple that with a structural analysis, but the contacts within here, when I develop contacts and create a contact between something and something else, so I'll create a contact between this and say this, and create that contact, you'll see in here, when we're doing motion analysis, I can enable friction and specify both the static and the dynamic coefficient of friction, and when we transition from the stiction, as they call it, when we transition from static to dynamic. So I can actually get a very accurate representation of friction if I'm doing a motion analysis. And the motion, unfortunately, would take an entire hour and a half on its own to go in. But that Altair University website I showed you right in the beginning is going to have a ton of data on how to do motion analysis, or if you get in touch with us by registering for a sponsorship using the methods I showed you, we can arrange custom classes for you, even visitations, to help you use the motion analysis, which can then be coupled with analysis and optimization as well.
Thank you so much, Eric.
Yep.
Question that came in, and maybe you can help, because I'm exactly sure what it refers to, but is this archive able to down?
I'm sorry, Norman, could you repeat that? You broke up there.
Is this archive able download? So what the question is probably referring to is either the material that you've shown, is this available as tutorial material?
Yes. So again, if you go ahead and register for us with sponsorship, we can that way we can contact, or you can contact us. You'll be given a contact name. It may even be me. I can get you this material. Also, much of this is available on the Altair University website. But through a sponsorship, we'd be happy to get you the full course. Every single model I have here is from our standard 1 or 2 day Inspire class, and we'd give you all of the models and the step-by-step instructions to do all the exercises. So please hop on there. It's a free sponsorship, and it's our path to knowing that you're interested in the software, how we can get you that that material. Plus, we've got a ton of videos on the website, and I can send you videos, full classes that you can build your knowledge off of that as well.
Yeah, and if you were referring, and some of you have asked the questions, are the PPTs that you showed at the beginning available? A recording of this cast in the presentation, the slides, and the Q&A will be available on YouTube. You will receive the link through it if you have registered for it prior, so you can rewatch this presentation and, of course, share it with your team members, with the teammates, and anyone in university who might have an interest in learning more about Altair Inspire.
Yeah. And Norman, Eric, before you go on to the next question, just to let you know that those PowerPoints that I showed at the beginning, they are part of the training class package. So if you get that from us, you'll have those by default, even beyond the videos. So yeah, they're part of that.
That's great. Thanks for mentioning that. Another question that has come in is asking, if you modify a part from another CAD software, are those changes reflected in the part itself when you open it in its original software?
No, we don't have any bidirectional capabilities between the two softwares. In fact, most CAD packages these days have parametric design or a design history. In Inspire, we use, and I'm not totally fond of the name, but the general name for it is what we refer to as a dumb solid. And a dumb solid is just that. It has no history. It has no parameterization. So it just, whatever the state the model was in when you finished in your CAD, that was going to come in with Inspire. And the only way to get geometry or alter geometry back into the CAD system is to take that altered geometry or that optimized part, create that polynerb, and then save it as a parasolid step or IGES, and we can bring that back in. But we have no bidirectional communication at this time.
Okay, that's clear. Thank you. Just a reminder, folks, if you need more clarification or some tips, keep questions coming. Let's put Eric to the test here and see what he knows about the software and what his limits are. Eric, one question that has come in. Can we use Inspire for more than casting and additive parts, so specifically for sheet metal and tubing?
Yes, absolutely. So we do support the importation of surface geometry. So if your CAD model is surface geometry, it's going to come into Inspire as surface geometry, and then you'll have the additional requirement to go into that part in the model browser in that property editor over there on the left-hand side of the screen. And there will be a little field for thickness, and so that will allow to then calculate the mass of that. And any solid will be meshed in the background with tetrahedral elements. Any surface geometry will be meshed with quads and triads, if you're familiar with those type of elements. And then we can perform the same topological optimization. But we also, if you have surface geometry and surface mesh, then you'll have the additional capability of doing topographical optimization, development of a sifting bead structure. As for tubes, I've seen them done both ways, as surfaces or as thin solids that are like pipes that you see in geometry. So you can go either way, the surface or the solid geometry.
Now you have talked about the door hinge or the hinge assembly. Teams are interested in general more on an application question. What manufacturing methods would you recommend to develop those pieces with complex geometries?
So in a lot of ways, we're going to use the standard manufacturing, so maybe a casting. But even if we're not directly casting or stamping the part, we can still even use the manufacturing constraints within Inspire in it's like a CNC or a machined part. So if you imagine that the casting constraint indicates the direction that you're allowed to design in because it has to come out of the die, if consider that exact same thing, but consider it now as the direction that your machining tool is going to come in, the casting or the draw split or the single draw simulation represents a one-sided machining, and the split draw represents a two-sided machining. Well, we can't get as complex as, say, a six-axis machine. We can, to a certain degree, design or incorporate the capabilities of the manufacturing constraints into the machining design as well. And then if you've got, a really nice SLS metal 3D printer out there, leave them all off and go to town and come up with a really amazing design that can only be manufactured by additive manufacturing. Many of our corporations that we work with are doing it right now.
Mm. And while we're on the manufacturing, is the Altair software able to export directly into softwares?
Not directly into CAD stores. So the CAD companies tend to be rather possessive.
Sorry,
CAM.
sorry. I think the question is CAM. So can you basically upload it straight to your machines?
Unfortunately, I'm not 100% familiar with the version of file that a CAM software is going to look at. What we can export are Parasolid, STEP, IGES, and STL files. So if your CAM software can read any of those, then great, we're good to go. Otherwise, you'll need to do whatever you would do to bring it in there. I will tell you, STL is the standard format for bringing into 3D printing, so we got that covered. But as I'm not 100% familiar with the software, with the formats that a CAM software is going to use, I can just tell you what we can export, and hopefully you can take it from there. Not you, Norman, but the people who are asking the question. So.
And as you mentioned 3D printing, there is also one question. Under the material types, are plastics available that can be commonly 3D printed? Along with this, it'd be incredible to have the ability to optimize infill and shell parameters with a 3D printer.
Okay, so two things there. First of all, if you took a quick look at the material library, you'll notice the very two bottom ones were plastic ABS, which I'm sure if you're familiar with 3D printing, you're familiar with the ABS, and plastic nylon. And we can very easily add PLA in there if you're printing with that. What a lot of people do is they will actually print out a test coupon and pull it, and with some rudimentary machinery, you can relatively accurately determine the parameters of your 3D printed material. The one problem that we have is it tends to be on a case by case or printer by printer basis, because a lot of the structural properties of the 3D material that you're using are going to be substantially different when it's in its original filament form, and then depending upon the heat at which you melted it, the amount of cooling that it allowed to have, whether you got fans cooling it, all of those things can affect the end result. Plus, there is a fair amount of porosity built into 3D printed materials. As they cool, you're going to have voids in there. So it's usually best to develop your 3D printed properties. If you're really, really concerned about structural applications, it's best to develop them by putting a test coupon and coming up with the actual properties off of your printer. But for just rough estimates, you can grab some rough values for PLA, and the ABS is already in there. For the second part of that question, one thing that we can't do right now, though it was brought up previously, and it's something I did make a promise I was going to talk to some of our developers about, is, because I had never thought of it before, is the ability to optimize infill and that sort of stuff. That since 3D printing is becoming such a huge part of our society and manufacturing in general, that would be a great thing to include in there. Right now, no, we can't. What it's going to do is it's going to optimize it as a solid part. You may end up with voids in the inside if it determines that's the best optimization, but it's not in any way taking any infill or any 3D printed parameters other than that overhang manufacturing constraint we have. But like I told group previously, I'm taking this as soon as we can get back to the office and get back to normal work. I'm taking that directly to our development staff because I think that would be a great addition to Inspire, and hopefully someday we'll see that in there.
Yeah. A more general question, what do you see as the typical workflow for using Altair to from design to part? So starting with traditional CAD, then Altair, then traditional CAD, and then to the machine, or how do you see this?
Yeah, I think you nailed it there. Well, we have the capacity to generate geometry within Inspire. We are not a CAD software and not trying to be one right now. So the tools that you have in your CAD software are going to be far more powerful. You're going to be able to generate geometry far easier, far quicker in your CAD package. And that's why we like to say partner with the CAD. So yes, you're going to start with your design in the CAD. When you've got your design, and whether you decide to take it to a design space or just kind of a good part design, you then bring it to Inspire. And we're going to develop our design space from that. We're going to fill in holes. We're going to extrude it out, create that nice big block of volume of material, or that could have been done in the CAD. We're going to run the optimization in Inspire. We're going to allow that simulation-driven design to take over. Maybe we're going to run a couple of multiple analyses, maybe one with a stiffness, maybe one with a minimized mass. Take the ideas from both of them, create that polynurb geometry, bring that back into the CAD package, and then use the strength and the power of the CAD package to create that high-end design in the place where it belongs. The analysis belongs in our software because that's what we're excellent at and that's what we pioneered. The design belongs in the CAD software because that's what they're excellent at and that's what they've pioneered.
Mm-hmm. Thank you. Another question that has come in is, when you have your final design, can Inspire render it to make it look like a realistic part?
Okay, that's going to be one of those yes and no questions. So I say, no, the software that I showed you today cannot render it. But Inspire is becoming kind of a broad name for us. Inspire, when it was created, was so revolutionary and so widely accepted and so widely loved. We've taken this interface and we've broadened it out into a number of other companion products. In one of those is a companion product called Inspire Studio. Inspire Studio is about the closest thing we're going to have to a CAD package. It's an industrial design package, in some ways NURB-based. I refer to it more as kind of like the artist's CAD. Whereas we're going to talk a CAD package, I want this to be 25 millimeters from here to here, and I need this to be a 37.2 degree angle, and blah, 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 as engineers think. The Inspire Studio is more of a, okay, I'm going to grab this, and I'm going to pull on this, and I'm going to extrude this out and tuck this in here. So it's kind of like the artist CAD package. But what it really has is an absolutely phenomenal rendering package. It can render and create absolutely amazing photorealistic designs. So you're going to take that geometry, you're going to send it to Inspire Studio, and from that you can render it in there. It's a couple of steps where you assign a material to it, you assign some lighting and some of the more advanced parameters of it, and depending upon the size, the complexity, and the resolution you're looking for, you can get an awesome rendered package. And if you allot me about 15, 20 more seconds here, if you use Inspire Motion, you can actually export the motion into Inspire Studio, and you can render a three-dimensional motion in photorealistic. So that airplane flap that you saw, we could see it as if it were a shiny aircraft wing going through the entire motion, even seeing potentially the stresses on there in photorealistic rendering.
Okay, that's very clear. Thank you. And you can have as many seconds like, Eric. That's no
Thanks.
problem at all. And having learned about all these, and let me pass it to you as a final question for today about all these abilities and these functions of Altair Inspire. Is the software actually used in really large companies in industry?
Oh, absolutely. I would say so. We've got something in the neighborhood of 8,000 different clients, and I would say the vast majority of them are using Inspire in some way or another. But just to get into the specifics, I have directly taught customers at SpaceX, at Blue Origin, at NASA, GE Aviation, Ford, Harley Davidson. Uh, the list could go on, and they are today using Inspire to generate amazing 3D parts and designs that they never would have thought imaginable because of the ability to do metal 3D printing these days. So yes, our corporate customers are doing it. And just to let you know, there was a little birdie whispering in my ear, letting you know or wanting me to let you know that the Inspire Studio and the entire suite of Altair softwares is available with the sponsorship. And actually also with the free student edition, so you can render with that by getting the student edition and or the sponsorship.
Great to know, Eric. And with that, I would like to really thank you for spending the time today with us, giving this very insightful presentation and addressing all the questions that we had today. It was amazing to have you and the whole Altair team, and thank you for supporting Shell Eco Marathon. And thank you again also to our students tonight and the participants of Shell Eco Marathon for tuning in and taking part in this webcast. There are more virtual learning sessions coming up in May. Tomorrow, you'll be hearing from Eric again about meshless analysis. So if you haven't registered for any of these webcasts, please do so on our website. We'd love to have you join. Thank you again for tonight. Thank you all for joining, and have a good night. Bye-bye.